Welcome to the Cosmos Enthusiasts. Today, we're diving into an incredible revelation from the James Webb Space Telescope that's sending shockwaves through the world of cosmology. If you're fascinated by the mysteries of the universe, buckle up. This discovery is a game changer. Peering into the universe through a telescope is akin to traveling back in time due to the relatively slow speed of light. Light from stars in our own galaxy, both nearby and far, takes years, even millennia, to reach us. This means that viewing distant galaxies is essentially glimpsing into the universe's history. This context highlights the significance of discovering the most remote galaxy yet, which is also the oldest known. Just 2 years ago, in 2022, the Hubble Space Telescope held the record for detecting the furthest galaxy, named Gien's 11. This galaxy's light journeyed to us from a time only 400 million years post-Big Bang, when the universe was a mere 3% of its current age. However, the entry of the James Webb Space Telescope into this cosmic quest shattered Hubble's long-standing distance record. With its superior size, sensitivity to different wavelengths, and an advanced suite of instruments, James Webb exceeded Hubble's capabilities repeatedly, pushing the boundaries of our cosmic historical knowledge. Within its first 2 years of operation, James Webb has repeatedly outstripped Hubble's records, relegating Gien's 11 to 9th place in the ranking of the most distant galaxies, a position it held at the time of Webb's launch. Numerous observations of the galaxy Gien's 11 were planned for the initial year of the James Webb Space Telescope's Webb operations. As a result, Webb has dedicated dozens of hours to meticulously studying this galaxy, a significant allocation of its valuable observation time. However, the data obtained has not been as straightforward as anticipated, leading to a debate between two groups, one based in Cambridge and the other in Oxford. The disagreement centers on whether Gien's 11 hosts a growing supermassive black hole. The script invites the audience to explore Webb's data, and this debate over one of the universe's most distant galaxies, a key to understanding both the cosmos and our place within it. This understanding was revolutionized in the 20th century with the discovery of the universe's expansion. The fabric of space can be likened to a ball of rising dough, with galaxies represented by raisins scattered throughout. As the dough expands, the raisins, or galaxies, move further apart. From the perspective of an observer in any galaxy, other galaxies appear to recede, with more distant galaxies moving away more rapidly. This results in the light traveling between galaxies experiencing greater effects due to this expansion. In this script, the focus is on the shift in wavelength of light from distant galaxies. It explains that detecting light of certain wavelengths requires specific types of telescopes and detectors. Longer, redder wavelengths, which correspond to lower energies and cooler temperatures, necessitate telescopes and instruments capable of operating at sufficiently cold temperatures. This is essential to distinguish the low-energy light from various forms of noise. While the Hubble Space Telescope can observe light up to about 1.5 microns in wavelength, the James Webb Space Telescope, due to its cold, cryogenic design, can detect light up to 20 times longer, reaching 30 microns in wavelength. This capability enables it to observe the most distant and reddest objects in the universe. The script also highlights that in its very first release of scientific observations, the James Webb Space Telescope discovered a multitude of extremely red objects. However, it cautions that not every red object is a distant galaxy. There are numerous factors that can create similar signals, such as galaxies where the hotter, blue massive stars have expired, leaving only the redder stars, or galaxies abundant in dust grains. These factors can mislead observations, underlining the complexity of accurately identifying distant galaxies. This script explains how certain galaxies can appear red due to various factors. One reason is the presence of dust grains of certain sizes that block bluer light while allowing redder light to pass through. Another is the position of galaxies along a line of sight that scatters or blocks blue wavelengths, leaving only red wavelengths. This phenomenon presents a challenge in astronomy, particularly with photometry, a basic technique used to measure the color of an object. Human eyes have three types of cones sensitive to red, green, and blue colors, and similarly, telescopes are equipped with multiple filters sensitive to different light wavelengths. When observations show no light in the shorter wavelengths, but a significant amount in the longer wavelengths beyond a certain point, the object becomes a prime candidate for being an ultra-distant galaxy. However, such an object is only a candidate at this stage. Its red appearance might suggest it is seeing extremely red-shifted light, but this needs to be confirmed with more definitive data. Confirming the distance to an object that appears extremely red involves analyzing its galactic spectra, a task where the James Webb Space Telescope excels. Through this analysis, astronomers can accurately determine the galaxy's actual distance, distinguishing true ultra-distant galaxies from other red-appearing objects. This process is crucial for understanding the true nature and distance of these cosmic objects. The script describes how the James Webb Space Telescope, Webb, uses infrared light to study the universe. The light collected by Webb is redshifted, meaning its wavelengths have been stretched during their journey across the cosmos due to the expansion of space. The degree of this redshift helps astronomers determine the distance of a galaxy and the time when it originally emitted its light. Nearby galaxies exhibit almost zero redshift, but Webb is adept at observing objects beyond a redshift of 5, equivalent to about 1 billion years after the Big Bang. Higher redshifts indicate galaxies that are both older and farther away. The script then explains how spectra provide insights into galactic activities. Different hues in the spectrum represent interactions between photons and various atoms or molecules. For instance, one color might arise from a hydrogen atom emitting light as it stabilizes after being energized, while others could indicate excited oxygen or nitrogen atoms. A spectrum is essentially a collection of colors that reveals the composition of a galaxy and the behavior of its elements. Webb's ability to capture spectra provides essential information about galaxies at distances never before reached. Additionally, galactic spectra are invaluable in identifying major disturbances in atomic structures. This script discusses the role of the James Webb Space Telescope, Webb, in studying giant black holes located at the centers of galaxies. While black holes are inherently dark, they emit telltale signs when consuming gas and dust, as they break down atoms which then emit characteristic rays. Before Webb's historic launch, astrophysicists were hopeful that the telescope would aid in detecting these patterns, helping to locate some of the earliest and most active supermassive black holes in the universe. This, in turn, could provide clues about their formation. A significant breakthrough was achieved by Webb, which, as reported by a research group from the University of Cambridge, led to the identification of the oldest black hole ever observed. This ancient cosmic giant, with a mass around 1.6 million times that of our Sun, is situated 13 billion years in the past, a mere 440 million years after the universe's inception. Located at the heart of the early galaxy Gien's 11, this supermassive black hole was revealed through Webb's advanced camera capabilities, designed specifically to explore the origins of the universe. This observation not only uncovered a solitary cosmic abyss, but also revealed a multitude of black holes that experienced rapid growth during the cosmic dawn, around 100 million years after the Big Bang. These black holes illuminated the young universe for a billion years, shedding light on the mechanisms driving their rapid expansion and providing a clearer understanding of the early stages of the universe's evolution. The script delves into the enigmatic rapid expansion of cosmic vortexes, or black holes, in the early universe. The mystery of this swift growth remains unsolved, but understanding it could shed light on the development of contemporary supermassive black holes, such as those at the center of galaxies, including our Milky Way. Roberto Gilli, an astrophysics professor at the University of Cambridge, posits that black holes in the early universe likely didn't grow gradually and steadily like their modern-day counterparts. Instead, they might have experienced unique origins and formation processes, leading to different growth patterns observed in the current cosmos. Astronomers believe black holes begin from the collapse of massive stars. They grow by consuming gas, dust, stars, and even other black holes. The friction from this consumption heats the spiraling material, causing it to emit light. This process turns them into active galactic nuclei, AGN, with quasars representing an extreme type of AGN. Quasars feature supermassive black holes, billions of times more massive than the Sun, emitting light trillions of times brighter than the brightest stars. The James Webb Space Telescope, equipped with infrared cameras, plays a crucial role in studying these luminous phenomena and enhancing our understanding of black hole formation and evolution in the universe. The script explains how the James Webb Space Telescope uses spectrographs to analyze light frequencies, uncovering specific signatures that indicate the presence of a black hole. This technique enables astronomers to detect the faint light emitted by the hot material encircling a black hole. The rapid growth of early black holes has several proposed explanations. One theory is that they formed from the sudden collapse of massive gas clouds. Another possibility is that they grew through mergers involving clusters of stars and black holes. There's also a fascinating hypothesis suggesting these black holes might have been seeded by primordial black holes, which are thought to have formed immediately after or even before the universe's inception. Roberto Gilli, the lead researcher, points out that direct collapse might not be the only pathway for black hole formation. For this to occur, specific conditions are necessary, such as a pristine gas cloud unenriched by heavy elements. Moreover, the cloud should be exposed to ultraviolet light, potentially from a neighboring galaxy or black hole, to prevent it from cooling too quickly and forming massive stars instead. The study implies that a combination of these scenarios could account for the varied origins of ancient black holes. Gilli and his team suggest that their findings not only explain the high luminosity of the galaxy GNZ11, but might also provide insight into the unique characteristics of other distant galaxies and black holes. This script outlines a debate over the high nitrogen abundance in the galaxy GNZ11, as observed by the James Webb Space Telescope, Webb. While some researchers, such as Roberto Gilli's team, suggest this points to a growing supermassive black hole, the Oxford group, led by Cameron Katz-Ray and Saxon, offers a different interpretation in their recent paper. Their study does not focus on the presence of a supermassive black hole, but rather explores alternative explanations for GNZ11's high nitrogen levels. The Oxford group argues that there is no convincing evidence to link the nitrogen enhancement in GNZ11 to enrichment from metal-free population, II stars. Instead, they propose that the unusual emission lines observed could be the result of runaway stellar collisions in a dense stellar cluster or a tidal disruption event. These scenarios could explain the similarity between GNZ11 and nitrogen-rich quasars. These findings highlight the new opportunities provided by Webb in studying galactic composition and stellar evolution within the first 440 million years after the Big Bang. However, the question of whether GNZ11 harbors a central supermassive black hole remains unanswered. This ongoing debate exemplifies the chicken and egg dilemma in understanding the formation and evolution of such cosmic phenomena. This script discusses a fundamental question in cosmology: which came first, the giant black holes or the galaxies they inhabit? Answering this could unlock the secrets of how the earliest black holes and galaxies formed after the Big Bang. Astrophysics benefits greatly from the collaborative use of multiple telescopes, each operating across different segments of the electromagnetic spectrum. This comprehensive approach has been crucial in understanding the true nature of various mysterious celestial objects. To further our understanding of black hole populations in the universe, X-ray observations are now needed. While they may not be as visually striking as optical images, X-ray data can reveal the most extreme cosmic events. For example, a supermassive black hole consuming vast amounts of gas and dust produces a significant amount of high-energy X-rays. Detecting even a few X-ray photons from GNZ11 or similar galaxies would strongly indicate the presence of a supermassive black hole, providing crucial information about the timing and mechanics of cosmic evolution. Currently, there is no facility capable of performing these highly demanding observations. The existing major X-ray telescopes, Chandra and XMM Newton, have experienced significant degradation over time. This highlights the need for new, advanced X-ray observatories to continue pushing the boundaries of our cosmic knowledge. The script explains that the current major X-ray telescopes, Chandra and XMM Newton, launched over 2 decades ago, lack the sensitivity required to detect black holes smaller than about 1 million solar masses in the distant cosmic regions that the James Webb Space Telescope, Webb, is exploring. This limitation underlines the necessity for a more advanced and powerful X-ray observatory to deepen our understanding of how black holes evolve in space and time. Such understanding is vital, as it builds on the legacy of human achievement represented by successive generations of exceptional space telescopes. This need for advanced observatories is why many astronomers are already thinking beyond the projected 20-year lifespan of Webb. They are envisioning a new series of major observatories, each specialized in detecting different types of light. Ideally, these observatories should be launched in quick succession around the time Webb's mission concludes, to ensure a continuous and overlapping time frame of operations, maximizing the scientific yield. The original Great Observatories program, which began with NASA's launch of the Hubble Space Telescope in 1990 and included Chandra and 2 other, now retired space telescopes, the last launched in 2003, serves as a precedent for this approach. Following the recommendations of the 2021 Decadal Survey by U.S. astronomers, which is mandated by Congress, there is a plan to develop a trio of new space observatories. This ambitious plan aims to continue and expand upon the legacy of space-based astronomical research. This script outlines ambitious plans for future space observatories. The first of these, named the Habitable Worlds Observatory, is slated for launch in the early 2040s. Its mission is to study potentially Earth-like exoplanets and other celestial bodies using optical, ultraviolet, and infrared light. Following this, 2 more observatories are planned, one specialized in X-ray detection and another for far infrared observation. These could be launched later in the 2040s or even in the 2050s. Collectively, these observatories aim to provide a more comprehensive and vibrant view of the universe, potentially heralding a new golden age of space-based astronomy, about half a century after the launch of the Hubble Space Telescope. The proposed X-ray observatory, in particular, is expected to be capable of detecting growing black holes as small as 10,000 solar masses within the early galaxies observed by James Webb. This represents a 100-fold improvement over the capabilities of the Chandra X-ray Observatory. However, the realization of these plans faces potential challenges. These include fluctuating political support, unforeseen technological hurdles, and the constraints of NASA's extensive portfolio. There's a risk that these factors could slow down the development and funding of the project, leading to longer intervals between the launches of these new observatories. Such delays could diminish the likelihood of their concurrent operation and, consequently, their overall scientific impact. This script discusses the financial challenges involved in launching 3 new space facilities by 2045. Achieving this goal would necessitate doubling NASA's astrophysics budget throughout the late 2020s and into the 2030s. However, as of now, there is as much evidence supporting such a budget increase as there are X-ray photons detected from distant galaxies, essentially none. In fact, the latest budget proposal from the administration suggests only a 3% increase in funding for NASA's Astrophysics Division for the fiscal year 2024. Despite the substantial investments already made in the James Webb Space Telescope, Hubble, and their related projects, which have sparked a scientific revolution, the United States and its international partners must maintain robust, ongoing support to realize the full potential of space science. This commitment is crucial, not just for answering current questions, but also for addressing new ones that may emerge in our quest to understand the cosmos. The script highlights that the mysteries surrounding black holes, celestial entities that devour worlds and stars, have long captivated both experts and the public. To continue exploring these fascinating phenomena and to maintain leadership in space science, it is imperative to support the next generation of observatories. Welcome to Blazovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blazovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe. Live Q and a sessions with experts. Your membership will grant you the chance to participate in live Q and a sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blazovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.